Hey, welcome back to ECE 382, Module 4, Software Design. So we're going to be moving into C coding. So we've spent the last couple lessons looking at assembly. That's kind of the foundation of our code. Now we're going to take it up to the next level, coding language C. You've seen C in Comp Sci 210, but we're going to look at it a little bit of a review, mostly just looking at a lot of the different syntax. And then we are going to also apply it to a little bit of what we will be doing in this class. So this first video, part 1, is just looking at C coding. It's going to be due prior to lesson 6, and then there's going to be 2 more parts to this module, and those 2 videos will be due lesson 7. So let's get into it. So C program, we're going to start with logic operations, just like we did with assembly, and the use is going to be primarily the same. 4 different things we're going to be trying to do. We're going to be trying to select certain bits, clear bits, select, clear, and set, and then lastly toggle. And then sometimes we will combine bits. And so we use these when we are trying to take inputs and outputs. Again, talking about those ports on the MSB432, those ports are connected directly to sensors, motors, etc. And so there's certain times where we're just interested in a certain pin on that port. So for example, port 1, bits 1 and 0. So that's port 1, pin 0, port 1, pin 1. And if we just wanted to select and see what the input of those 2 bits were, we can use this example right here. So we are going to set the input, the values coming in on those pins, and we're going to look at just pin port 1, 1 and port 1, 0, and we're going to set that to Y. So Y would be the value. And say those are connected to our 6 bump sensors. These might be connected to port 1, and then this would be pin 0, 1, 2, 3, 4, and 5. So Y would be the value of these 2 bump sensors right here once we select those bits. So that's what we're doing with the ANDing with 1. So just remember, if we want to select bits, and with 1. Same thing we did with assembly. We're going to clear bits, so maybe this is an LED. So say we have 4 LEDs. And those are connected to pin 2, 0, 1, 2, and 3. We can turn off those as an output and turn off those LEDs by ANDing with a 0. And remember from logic from 281 that these and with 1 and 0, we know what those do. Anything ANDed with a 1 is going to be that initial value. Anything ANDed with a 0 is going to be a 0. So that's why we can use those AND values to select and clear bits. Now if we want to turn off those LEDs, so AND with 0 is going to turn them off, or with 1 will turn them on. So this will turn them off, these will turn them on. So we could say and if we want to just turn off bits 0 or LED 0 and 1, we will AND with a not 0x03. All right, so what's going on here? So 0x03, what that is 0, 0, 0, 0, 0, 0, 1, 1. And when we take the NOT of it, we now have 6 ones and a 0. And when I AND the previous values, what I'm doing here, say previously LED 3, that one was on, and LED 2 was on, but these two, let's just say they were all on, but we only want to turn off 2 of those. So previously, the port 2 values equaled, and we're going to just ignore, we don't care about the first 4, but they are 1, 1, 1, 1, right? And if we want to just turn off these 2, we don't want to just set them all to 0 because then we'll be turning off all 4. So we can use this kind of cool little technique here where we take the 2 bits we're interested in, we invert them, so we take the opposite, then we AND it with that. So now we get this value here. We're going to AND our previous value of, and we don't care. The next thing is we'll maintain everything, and the output of this is still don't care, 1, 1, so we're ANDing, remember, and then 0, 0. And so now what we're going to send to port 2 is going to be turning off that LED and that LED, but keeping these 2 on. So we've met our requirement. We only wanted to turn off 0 and 1 without changing the rest. We'll see this later called friendly programming, where we only change the bits that we're interested in changing, and we leave the other bits the same. So that's what we did here. We only changed these 2 bits, and we left the other 6 bits of the port exactly what they were before. And that's important because sometimes we don't know what these ports are connected to, or sorry, these pins are connected to, and they could be connected to something that's driving the motors or doing something else in the background. And so we want to make sure that we don't just set everything to 0. And that's called friendly programming, and it's really important. So we saw selecting, clearing, and setting. So again, clear is AND with 0. Setting is ORing with 1. And the last one is toggling, and that's where we get that exclusive OR with 1. And we can see here the different symbols we use, and just move this over just a little bit. So AND is singular ampersand, ORing is the singular vertical line, and then exclusive OR is going to be that not equal, or that caret equal. And this example right here shows us combining 2 bits. Or sorry, 2 x bit numbers. So what we can do there is if x might equal 0x 1 2 3 4 1 2 3 4, and then y equals 0x 1 0 0 0 0 1 2 3 4, and then now z, we can combine those, and z is going to equal all ones. Okay, so those are our basic our basic logic operations. And we spent a little bit more time on that than other things in C programming because this is one of the key things we're going to be doing. We're going to be interacting with hardware that's connected to pins, and we're going to be specifying specific pins that we want to turn on and off, or that we want to read from. And so that's where all of this logic operations, these ANDs, ORs, and exclusive ORs are key. You have to understand these different commands and know with confidence what you're doing when you're doing one or the other. All right, let's move on to shift operations. Same thing we saw with assembly. We got logical arithmetic shifts right, and then the logical shift left. The key thing here is if something is going to be sign extended, arithmetic shift left, we have our sign extend, which is, arithmetic shift right, which is our divide by 2. Logical shift right, we're just going to throw in a 0, we're just shifting the bits. And then logical shift left, we're going to multiply by 2, or again, shift bits. And we'll see this potentially come in with our bump sensors, because there's 6 bump sensors, but they're not connected to 6 side-by-side pins. And so if we want to look at the state of the bump sensors, we're going to have to potentially shift some of the pins. So I can't remember off the top of my head, but it would be nice if it was 5, 4, 3, 2, 1, 0, but I think it's something along the lines of more like 7, 6, 3, or maybe 2, 1, 0, or maybe one's from a different port entirely. And that comes down to what works when they designed this robot, how the pins all lined up. I did not design that, so we'll mess with that later in one of the labs. All right, arithmetic operations, just know they exist. You can Google them. You've seen them probably in Comp Sci 210. We will use them a little bit in this class, but here are some of them that you will see. All right, let's talk about conditionals. So in C, for Boolean, true or false, basically, 0. Let's go back to my nice red pen. 0 is false. Non-zero is true. And then remember, instead of, we saw the ampersand and the vertical line before, but in conditionals, it's 2 ampersands. So that means, X and Z. This is our conditional and, conditional or, and then we can use the not symbol as our operators. So you can see the example of the not there, and here, or here. So we want to always compare similar types. Returns a Boolean. So one thing we can do, and this is kind of a hint for one of the first labs we do. So remember, 0 is false, but anything that's non-zero is true. So if we have our bump sensors connected, and there's 6 of them, so let's just say, conveniently they're located at 5, 4, 3, 2, 1, 0. So let's just say these 6 bits here represent our bump sensors. And the nice thing is, if any one of those is a 1, this comes back as true. And so we can just test if bump, then we know that there is a bump sensor pressed. And we don't really care which one at this point. We might down the road when we're doing more with the maze, but at this point in time, if there's any of these bump sensors are pressed, aka if it's a non-zero, then it's a true, and we can use that. So we also have our greater thans, our equals, our not equals, or sorry, greater than, less than, equal, not equal, all of those relational comparators. So for the conditionals, we have if else statements, and then we can also do an if, and it's else if with a space and else. and that helps us to kind of just do those different conditional statements. All right, functions. So functions in C, very much what you've seen before. You have your type, return type, name of function, and then your inputs. We'll have function declarations in the .h files, so function declarations. And we'll talk about what's in the .h file, .c file later, but those will always be in the .h files. Functions can call more functions, You've all seen C, so you know what we're doing here. All right, loops. Very straightforward. While condition, do something. Do whiles are the opposite. So a while checks condition first. And a do while checks condition last. So with for loop, key thing to note is in this version of C, you have to initialize the variable within the for loop. So you can't do int I and then do that. We can't do that. We have to initialize it within the for loop, and that's just the version of Code Composer Studio, the version of C Code Composer Studio is working with, and that's just how it works. All right, so let's talk about variables. This is big part of what we will be doing in this class are global variables. So you might have heard in Comp Sci 210 global variables are bad. While somewhat true, global variables can be bad. They are also very useful. So we'll talk about when they're good and when they're bad. So variables, globals, basically just declared outside a function. And there's two different types. So globals are they're allocated permanently and can be accessed from anywhere in the system. So, but we can define them in two different ways. So one is an external global, which is basically the idea that it's in a can be accessed in different files. Those are not good. So it makes it very hard to debug. It makes it hard to understand what the code's doing because you're working with a variable. You don't know where that variable is declared, so then you have to go look somewhere else. So external variables, bad. On the other hand, global variables that are within a file, we just call them, regular global variables. Those are very helpful. So internal global allows us to do a few things. And they're accessed and defined within same files. So that's fine. Sorry, in the same file. So there's two reasons. We use data permanence. So, for example, time. So every time a new function is called, we might want to observe the global time of the system. So that's data permanence. So it's permanent. It is permanent between functions, and so one function might change it, the other one might be reading it. So the big thing is you never want two separate processes changing global variables. Typically, always, one process will change it, and others will read it. Okay, so that's key. So two reasons to use internal global variables: data permanence, so such as time, and the other is to pass, so basically information sharing. So for example, you might have a file, or sorry, a process that is reading bump sensors, and you have another process that is driving motors, and then we have a global variable called bump, and this one here is taking and bump equals X, and this one is saying if not bump, so if we haven't hit a wall, drive. And so that's data sharing, and that can only be done with using global variables, because these are two separate processes. They can't just use a local variable. One, they don't share local space, and so using a global variable bump allows them to communicate. All right, local variables, we know what those are: temporary information within a function, private global, and so this is more of what we're using with this internal global. So these are very similar, but these are only used within the same file. And then static local has more permanent memory allocation. And then we'll maintain values between calls, but still only accessible within functions. So the two we'll primarily use are these global and static, or sorry, global and local, maybe static global. All right, last two things to talk about: constants. Well, three things, I guess: constants, switch statements, and arrays. So let's talk constants real quick. So, so think of pound define as a macro or a preprocessor directive. And this is going to allow us, basically every time we use the word OK throughout our code, when the C code is compiled, it's the processor is going to take OK and replace it with 0. It's going to take left and replace it with 1, so on and so forth. Bad thing of these, let's just say downside, constants do not have a type. So while this is acceptable to do, and we do it frequently, it does not have a type. So using the constant keyword provides us a little bit more capability to provide type checking. So this one provides type checking, and then we have a more secure system. All right, but the most well-defined is the type, so enumerated. So what we're doing here is we're basically creating our own set of variables. And so an example you see here, the type def operation, so this guy right here, creates a new data type. And it's restricted to values that we see up here, which are OK, left, and right. When we use this enumerated mode here. And the nice thing is now we are restricted to values we want. And so we think about this with our maze. So we could have a straightaway, a left turn, a right turn. So we could assign all of those to different values, such as 0, 1, 2, 3, so on and so forth, which is exactly what we will do. And then we can create create this mode T variable state. We can set it equal to OK. We can do all the things we would normally do with different variables. So if state equals right, there's a right turn, turn right. I wish it was this easy, but it's not quite. And what this allows us to do, it just makes the code so easy to read. And it also at the same time protects our type checking. So it's really nice. We can create all of these different variables that we've and then we have this restricted capability. So we're going to use enumerated types quite a bit in this class, and hopefully you've seen them before. All right, two things left: switch statements and arrays. I'm not going to go into a whole lot of detail. These are just standard things straight from C, so there's not a whole lot to talk about. But these switch statements, this is just the syntax for them. Case statements always include a default just in case. And then the last are your arrays, just showing examples of how to define different 1D and 2D arrays so that if you need to do that, you at least have this resource. So that's it for this lesson video. 2 more videos for this module, but we're going to stop here. That's all that's due for the next class, along with the pre-lab. So you're going to work on the pre-lab, and that's going to set you up for the lab that we're going to do in class next time. Have a good one. Stay safe. Don't get COVID. We'll see you later.